Okay. My goal today is to help you guys solve a question like this. I'd be willing to wager a lot of money. They're going to give you a question like this in the diploma, and it's not going to be multiple choice, it's going to be written response, or like numerical response. Because here's the issue. If it's multiple choice, an easy way of solving it is taking the 4 answers and guessing and checking them until you get the right answer. Which makes it really easy. And so they often make a question like this be numerical response, which sucks. So I need to show you how to solve this. The first issue to a question like this is that the x as a variable is an exponent, which makes it tricky to solve. So I'd like to show you guys the method of how to solve this one first. So maybe just watch this first one. 8 is the base. I can write 8 a different way. 8 is also equal to 2 to the 3. Does that make sense? I can do the exact same thing with 16. 16 is actually also equal to 2 to the 4. Make sense so far?
No.
Okay, this 8 right here, 8 is actually 2 times 2 times 2. So I can write 8 as though it has an exponent. 8 is actually 2 to the power of 3, 3 being the exponent. 16 is 2 times 2 times 2 times 2. So I can write this base as though it has an exponent. Here's how this looks then. 8 is actually 2 to the 3rd, and then you still have the 3x minus 2 afterwards.
So it's multiplied, not like
It actually multiplies.
Then can you distribute it?
Good, I'm going to do that in a second. Bear with me though. 16 is 2 to the 4, but there is also an x plus 1 there.
Oh, that's the base.
Good. 2 things here. Learn me, you've got both of them. 1, they have the same base, which really means the base can cancel. And what you're left with is 3 bracket 3x minus 2 equals 4 bracket x plus 1. And then the second thing that you pointed out,
are those still exponents?
well,
Doesn't make a difference.
doesn't make a difference anymore. Yes, they were both exponents, but this exponent here is now equal to this exponent here because these bases have canceled. This guy has a base of 2. This guy also has a base of 2. Cancel the bases. Why not? What if I gave you 3 to the x equals 3 to the 2? What's x going to be?
2.
Why? Well, cancel this 3. Cancel this 3. Look, x equals 2. So that's what I've done here is I've canceled the 2's. So last thing here is I can expand this now. So this 3 that came because it was 2 to the 3, it has to multiply. So you'd actually have, let me erase this stuff here. So 3 times 3x would give you 9x. 3 times minus 2 would give you minus 6. 4 times x will give you 4x. 4 times 1 will give you 4. Ready?
So we can back up how we got to that 3x.
Sure. So this 3x minus 2 came from right there. And then this 3 right here came because it was 2 to the 3. So rather than writing this 8 right here, I'm writing it as 2 to the 3. And so the 2 gives an exponent of 3, but the exponent of 3 combines with the already there exponent of 3x minus 2, and we expanded them.
Oh, okay.
Does that make sense? Okay. Last step then, minus 4x, 5x minus 6 equals 4, add 6, add 6. 5x equals 10, divide by 5, divide by 5.
But you have
No, it actually isn't.
What if you can't find like common bases?
Okay, I have a solution for that later. You're a little ahead of me, but yes. Can you check your work?
Yeah.
Should be able to. You shouldn't get extraneous solutions, just so you know, but you should still check. Let me just do this here. 3 to the 2 would be 6. Minus 2 would give you 4. So if anyone has a calculator, can you tell me what 8 to the 4 is? What'd you get? Okay. And then if you do 16 to the power of 3, hopefully that's also 4096. Is it? 16 to the 3?
It is. So, X. Wait, why did we do x to the 4 and 16 to the 3?
So I'm just checking my work. If x is supposed to be 2, then I'm plugging 2 in right here and 2 in right here, just to make sure that it was equal. Let me just erase that, and I'm just going to try it one more time just to make sure that you guys catch the steps here.
It's such an easy.
It actually is not that hard.
Do we get it harder though? Like,
Well, yes, there are other tricks you can play, but... So, step 1. This base right here is not the same as this base right here. So our goal is going to be to make them the same base, and then we can cancel those bases. So 8 is actually 2 to the 3, but there's still that 3x minus 2 up there. And 16 is 2 to the 4, but there's still that x plus 1 up there. Now that they have the same bases, the bases can cancel. So what you're left with is 3 with the 3x minus 2, the 4 with the x plus 1, and now FOIL and simplify. So 9x minus 6, 4x plus 4, and then what did I do? I minused 4 from both sides. I added 6. So I got 5 with 10 and divided by 5. Does that make sense? Here I just got a generic slide. I want to discuss how this relates to other stuff we've done. Okay? I need you guys to know how to solve a polynomial function. So back in the unit 1, how do you solve a polynomial function? Well, you have to be able to factor it into like a whole bunch of bracket stuff. I also need you to know how to solve a radical function. So a radical function, if there's a square root, to solve that, you square both sides. That sound familiar? I also need you to know how to solve a rational function, which means you need common denominators. So like these two guys right here do not have common denominators, but if I times by x plus 2 over x plus 2, and then do some cross multiplying, you might be able to solve this guy. This is kind of the same thing here. If I give you an equation involving exponential type stuff, you're going to need what's called like bases. Why do we call them like bases? Well, that number has to be the same. I have a way of solving that later. Okay, so at least for today, everything we do will be a like base. So, there is also one more possibility which you may like. You could also solve these things graphically. Okay. What you could do is take, where was this equation? These guys right here, and type in y equals 8 to the 3x minus 2. Type in y equals 16 to the x plus 1. You could type both of those in your graphing calculator and see where they cross. That also would work. So like that I have right here, if you actually wanted to, you could graph one of them, graph the other one. They're both exponential functions, but like you could find where they meet. That also works. Yeah, they would meet where x equals 2. I actually have this on the slide there if you want to prove it yourself. Should we do that together as a class just to prove it? Sure. Okay. Grab your graphing calculators then. Go to your y equals screen. Get rid of everything else that might have been there from last week Friday. For those of you guys who were here on Friday, if you have a plot from the thing I showed you last week, turn it off. If you don't know what I'm talking about, I will show you in a little while. So then type in your two equations. So what was it? 2 to the power of 3x minus 2? No, it was 8 to the power of 3x minus 2, right? What was the other one? 16 to the power of, was it x plus 1? Is that what it was? The biggest issue with trying to solve exponential functions graphically is that, yeah, the window size is stupid. Here's what I got when I plugged the two of them in. Did anyone else get graphs that look like this?
Yes.
Yeah. Quick question. Why is this one graph right here kind of over there like that? This guy right here, x plus 1, what does a +1 after an x do to a graph?
Left.
Moves it backwards. That's one of the reasons why this second graph right here is over here, is because it's been moved backwards one. So, pretty cool. You have something else? Is your zoom set to zoom 6 like mine is, like a standard one? No, you've got a different zoom size, that's why. Anyways, you're going to need to change your window size. Or, to be honest, this may sound kind of weird, but you could intersect them even though you can't see where they cross. Your calculator will still do that. So like, try this. Go second, calculate an intersection point, and then just press enter 3 times. Like, once for the first curve, once for the second curve, and once for a guess. It won't actually show you the point on your graph, probably.
I like that.
But it should still find it, I think. Yeah. You could. In theory, this should work. Okay.
In theory.
Well, the diploma writers are excellent at finding ways to write questions where you can't use your calculator for whatever reason. So.
So you have to actually use maps.
Yeah. Okay. There is another way of solving then, which is what I just showed you. You could use like bases. Next week, I'm going to show you guys, well, actually it won't be next week anymore. It'll be like Thursday. There is also a way that you can use logarithms to solve these things as well. I'll show you what a logarithm is tomorrow and on Thursday. But let's try some more examples there. So here's what we want to solve. 27 to the x plus 3, 1 over 9 to the 2x minus 5. You could use your calculator. But I'm fairly confident that most of you can do that now without me showing you more than one example. So let's use it as a check. Okay. Let's start with the 27 then. 3 to the 3 works for 27, yeah. 27 is 3 to the 3.
Could that be 3 to the minus 2?
Well done. One more thing here then. Aiden already pointed this out. 1 over 9 is 3 to the minus 2. You want to explain why?
Because like when it's a decimal lower, negative just makes it smaller. So it's like the opposite. So like
It's called a reciprocal. Yeah, if you ever have a negative exponent, negative exponents mean 1 over top of 3 to the 2, which is 1 over 9. So this negative, like 1 over 9, is actually just means there's a negative exponent. So just put this off to the side. 1 over 9 is actually 3 to the negative 2. So let's write that. Yeah, let's write it as 3 to the negative 2, and then 2x minus 5. You guys have seen this before. And with practice, you'll remember it, I hope. Okay, so next step, cancel the 3's, so they're gone. 3x plus 9 now equals minus 4x plus 10. Add 4x to this side here. And that's where things are going to head to. Typically, these numbers here are not like nice even numbers. I got 1 over 7, which is probably like 0.28 repeating. I wasn't close then. Never mind. Yeah. Did that make sense? Cool. That's kind of the trick. Now the question is, can you solve, weirder, stupider looking questions? Like this guy. This is my last one, minus the word questions.
Can you straight up divide the 8 by 16 off to start?
Okay, well, a couple of things here. We got to review some exponent rules. First thing, can we give all of these common bases though? Could you guys handle getting everybody to a base of 2?
How do you know that there's a base of 2?
Hopefully after a while you kind of get used to like 8 is 2 to the 3, 16 is 2 to the 4, 32 is 2 to the 5. After a while, hopefully you'll recognize those numbers. So 2 to the 3, x plus 6. 2 to the 4.
So do all the bases cancel each other out?
Okay, that's the issue, is that they don't yet, but we have a trick to fix that.
But you think that you minus the exponents when you're dividing?
Well done. Who said that? Well done. Okay, so if everyone's okay with getting all of these to the base of 2, these guys right here are currently not able to cancel, but there's a rule you might have learned. Okay, if I gave you 2 to the 4 over 2 to the 3, the answer is 2 to the 1. The reason why is that 4 minus 3 gives you 1. Okay, or if I did another one, if I gave you 2 to the 3x divided by 2 to the 7y, this answer would be 2 to the 3x minus 7y.
Don't have the x's to like 2x minus 1 and x plus, don't they have to be the same too?
These guys right here don't have to be the same, they just have to subtract. So here's how that would look then. Just get rid of this stuff here. Since they have the same base, this is now 2 to the 3x plus 6 minus 4 to the 2x minus 1. And now we can cancel the 2's. So if you ever come across like a fraction, as long as they have the same base, you can subtract the exponents. The exponents don't have to be the same as each other or even remotely close. They just have to subtract. So now proceed, I guess. 3x plus 18 minus 8x plus 4 equals 15x minus 20. And just solve that. Let's see, 3 minus 8 is minus 5, and if I minus 15, I'm going to get minus 20x on this side. Right, minus 5, minus 20. And minus 20, that would make it minus 24. And then you're going to subtract 18 more.
I got 10
40,
of them.
42. And divide by minus 20. Divide by minus 20. So x is 42 over 20, or 21 over 10. Did you get that?
Yeah.
Okay. The reason why this is a plus 4 is that when you subtracted this thing from this thing here, the negative 4 has to distribute across the negative 1 to become a plus.
I distributed 4 and 4 was so yeah, but it's still
Um,
the same. So that's what I need to do, but and then subtract.
You do need to make sure you subtract those properly then.
I got it.
And x equals 21 over
21 over 10? Where did I lose you?
I'm just wondering why my math is not correct.
Do you agree with what I have in this line right here, the 3x plus 18 minus 8 plus 4? Okay, and then I brought all of the x's to this side, which gave me negative 20 on this side. I had 3 minus 8, which was negative 5, and I subtracted 15 more, so I got minus 20.
Oh.
Is that different than what you have?
Oh, then I'm not.
And on the other side, I had minus 20, and then I had to subtract 4, which I got minus 24, and I also had to subtract 18, which gave me negative 42.
They're on the same side. Just combine.
That's where I was. Okay. So, but it's plus 20.
Yep.
Yeah, 22 on the left-hand side.
Okay, that makes
Now you're alright. Why are you gonna do this with word problems?
Okay, so Aiden's looking ahead here then. To be honest, that's not my biggest concern for you guys, because you always have a backup method for solving this. It's not ideal, but you could, in theory, type them in your graphing calculator and find where they cross. Okay. The harder questions are word problems, and they almost always like to ask 1 or 2 word problems here. Typically, they don't even give you an equation. Okay. So I'd like to walk you through a couple of more word problems they may ask you to solve.
Will they give you that x equals?
No, I'm going to give this to you guys here for just right now. Okay. Before I do these word problems here, though, I feel like I need to go back and redo a couple of the word problems that I skipped in last day's lesson, which I did with a few of you guys on Friday.
We had a lesson Friday.
Well, like, we went over like 2 examples on Friday. Could you guys find the previous set of notes? Because we didn't finish everything in that previous set of notes. Can you guys go back and find this slide right here? I want to talk about this one first. We did this one on Friday, and I figured out why it didn't work. I had to look it up. Yeah, I do. Just gotta find where they are. Okay, one of the skills I need you guys to be able to have in this particular section here is if I give you some sort of word problem, you need to be able to make your own equation. And this is where I found, like in past years, this is where most students probably struggle the most. I don't think that exponential functions are really hard to understand in terms of like the graphs. This is my guess here. Like the graphs of exponential functions, they all look the same. They all go up like this or come down like this. Like they're all pretty similar. That's not the issue. Even solving them is usually not the issue. It's a question like this guy here. Okay. So for those of you guys who were here on Friday, I did this one Friday. Let me talk through it again with everybody else though. Okay. Here's a scenario. You've got a cup of water that's 100 degrees Celsius, and slowly but surely it's going to cool down to 20 degrees Celsius. If I were to sketch a graph of this, where it was like on this side here it was temperature, and this was time. If the graph starts at 100 degrees Celsius and ends at 20 degrees Celsius, would the graph be a straight line? I'd say that doesn't really make sense. The reason why is that if time kept going, then the cup would keep getting colder and colder and colder, and eventually it would become like freezing. That doesn't really make sense, right? Like, if I start with something at 100 and room temperature is 20, it should like level out at 20. So the graph should look more like, bear with me, this. It should start at 100, and it should slowly but surely end at 20. And what would happen at 20? You'd have an asymptote. Does that make sense so far? So we need to make an asymptote where x is 20, y is 20. Okay. How does that affect our function? Well, in terms of our function, where is the asymptote normally at? 0. How do I move it up 20? You add 20 at the end. If you were to take your function, whatever your function is here, and throw a plus 20 on the outside, would that not move the graph up 20? And by moving it up 20, would that not move the asymptote from 0 up to 20? Does that make sense? Okay. A couple other thoughts here. It mentions that the temperature decreases exponentially at a rate of 75%. If the temperature is going down by 25%, what are we keeping? 75%. I want to say that again. If we lose 25% of our temperature, how much temperature do we keep every time? 75%. So that's actually going to be our base, 0.75.
What?
Well, normally we go to the power of x, but here's a really important thing here. Every 5 minutes, it goes down that 25%. So the key to this then is you divide by 5. Because if x is 5, then 5 divided by 5 means you apply your exponent once. If x is 10, then 10 divided by 5 means you apply your exponent twice. Okay. One last thought. Currently, where is my y-intercept going to be?
We didn't have
Okay, well, where is normally a y-intercept of a graph?
Would it be 100?
No, normally the x-intercept is at 1. Sorry, y-intercept is at 1. Right, like your normal exponential graph. Normally your exponential graph, your y-intercept is at 1. But what happens when you add 20 to it? Okay, it's going to be at 21. But where do I actually need to start at? No, that's not the mistake we made last day, actually. Okay. We need to put an a value right here to stretch that y-intercept so that it starts at 100.
5.
We could. Logic, like what we did on Friday, though, for those of you who are here, this is our a value. It is 80. The reason why it's 80 is that if you stretch this thing up 80, the y-intercept would now be at 80. And then when you add 20, it would then go up 20 more and make your y-intercept be up at 100. So your graph would hopefully now look like this. Let me just sketch it. We'll throw it in our calculator. I figured out why it didn't work. I knew what I was doing wrong. I can explain it. So this graph here, I know. The equation was right. My way of explaining it was wrong. So this graph should start at 100, exponentially go down. By the way, why is the graph going down? What parameter affects that? This value right here, being a decimal, makes a graph decay.
A decimal
Lower than 1. Okay. And then this guy should level off when we get to 20. So let's just graph this in our calculator to make sure. So 80, 0.75 to the power of bracket x divided by 5, and then add 20. A couple of things here. If I do a zoom standard, I'm not going to see anything. Why? Yeah, at the very least, my window needs to go up to like 100 for y. So if I make that change, it's getting there. I need to change my x value too. So like, does anyone remember what we did for our window size last day? Like what our x value went to? Sure, let's go 30 then. Maybe I'll go even a little more than 30. 50? Let's go 100. I just want to make sure this works. There. That'll work well. And hopefully you get a graph that looks like mine does. Do you see how it's like leveling out right here? Right? It should be leveling out at 20. To confirm that, go second table set, make your table go to some very, very large number, and then go to your table and make sure that it's leveling out at 20.
How you explained it last time? It'd be like 75% of what we covered.
That was my issue, yeah. For those of you guys who were here last day, here's what else we did. I showed another trick where you can make your table set, rather than your table going up by ones. Do you see this thing where it goes like triangle table? That means what the change is in your table. Rather than having it go up by ones, which means that like on your table it's going to go 100, 95, 91, 90, whatever there. If I make my table set go up by 5s, then every 5 minutes, these numbers here should be going down. Okay. The difference here is that from 100 to 20, that's 80 degrees. What is 3/4 of 80 degrees? Yeah, 60. But then you have to re-add it back to the 20 degrees, and so that's why we're at 80 again. That's what I messed up on last day when I was working with you guys, is that I was doing 75% as though it was from 100 to 0, but it's not talking about from 100 to 0, it's talking from 100 to 20. And so it's 75% of whatever is left from there to 20. So this graph actually was the right graph all the way along.
Why does making table set randomly tell us where it goes like the same for?
Say that one more time.
Why does changing the table set to a really large number show us?
Well, because it's showing you what the y value is way in the future. Like I could keep going down and seeing what it gets close to. Even as I do this, it's getting really close to 20. But like a faster way of doing that is go to your table set and just pick a very large value to look up. And it'll start you there. So now I'm starting at a 10,000 instead.
Okay.
Colin.
Could you change like the table, change to like a decimal number, like 0.5?
You could if you wanted to, yeah. If that's helpful to you, absolutely. Okay, last question here, then we're going to take a break. This graph then has been translated and reflected and stretched. I need you guys to be able to explain what's happened. So like, for example, what does this plus 20 mean? Okay, so a vertical translation up of 20 units. Okay. What about this 80? What does that 80 do to the graph? Okay, so a vertical stretch by a factor of 80 over the x-axis. Okay. This 0.75 doesn't mean anything except that the graph is going to decay. So the 0.75 just tells you by like what factor it decays by. But there is one more number here. It's this over 5. Okay. What this really means is that you have 1/5 of x. So if you put a 1/5 in front of an x, it actually takes your graph and stretches it out 5 times as well. Does that make sense? So this x over 5 means pull your graph and pull it out 5 times further. So in terms of vocabulary, I'd say it's stretched 5 times horizontally, 80 times vertically, and then you moved it up 20 units. That makes sense? Okay. Go take a break. When you come back, I want to do the example in our new set of notes that's similar to it then, which would be this guy here, the bacteria one. Okay, so here's what I want to do then, guys. I want to focus on some of the word questions I need to be ready for. So here's a typical one. Bacteria starts with 3,000 bacteria, okay? And after 3 hours, it's now 48,000. The question is, how long did it take to double? Has it doubled? Yeah. Because if it doubled, it would be at 6,000. Has it doubled again? Well, yeah, because then 6,000 doubled would now be 12,000.
Has it doubled again, Larry?
Has it doubled again?
Yes.
So this thing has doubled quite a few times. Does that make sense?
How would you do that? You can't go, can you go like 48,000 times like 4 times?
Well,
If you look at it, though, it's divided like 5 times.
it's doubled 5 times. So 3,000 to 6,000, 6,000 to 12,000, 12,000 to 24,000, and 24,000 to 48,000. So we know it's doubled 4 times.
Divided by 3.
Okay, that'll work. I want to show you a way of using an equation as well, though. Okay. So, first thing, if this thing is doubling, what should the base be?
2,000.
If this thing is doubling, let's make the base be 2. Does that make sense?
You're way out there.
Okay. Okay, another question. If the bacteria started with 3,000, would that not be the y-intercept? Well, but the plus 3,000 at the end then would make the asymptote rise up, and it would work a lot better instead is if I put a number in front of it and did 3,000 there and stretch it up 3,000. Yeah.
Would it be x divided by 3 then?
Well, okay, here's where this gets tricky here. Normally, it would be x divided by 3 for those sorts of things, but that's not how this one's working. The 3 on the bottom typically refers to how long it takes for something to double. Like, let me go back to that previous example. It said that it every 5 minutes it cooled down, and so that we knew in 5 minutes it would cool down. Here, I'm going to tell you it's been 3 hours, but we don't know how long it takes. So it's 3 over x. And I put a little note down here in the bottom that might help remind you in case you ever get stuck. 3 over x. Okay, this exponent up in the top corner here, here's how it works. The top of the exponent is the total time that it's been. The bottom of the exponent is how long it takes for it to grow or decay. So we know that it has been 3 hours, but we don't know how long it's going to take. Does that make sense? Okay. Last thing here.
It could be like 2.5 hours.
Yeah, I don't know exactly how long it's going to take to double yet. We're going to solve for x. Last thing here, after 3 hours, the estimated count is 48,000. Where does this 48,000 go, though? Why? Yeah. 48,000 equals 3,000 times 2 to the 3 over x. Okay.
Oh, so if we divide by 3,000 and make the y equal a 2 base, and then
You've got the idea here. Okay, so a couple of thoughts here. These guys are not yet ready for common bases.
how the poop would you make that a common base though?
This, well, first we've got to divide by 3,000 like you suggested. This 3,000 right here, we got to get rid of it. So divide this guy by 3,000 as well.
16.
So 16 apparently equals 2 to the 3 over x.
Oh, then it's just 2 to the
Can that have a common base now? Okay. So 16 is 2 to the 4 equals 2 over 3x. Well, it would be 2 to the 3 over x, because we still have this 3 over x, 3 over x, 3 over x here. So then cancel the 2's. 4 equals 3 over x. And then how do you get x back by itself? Okay. Going too fast here. So it means that every 3/4 of an hour, it doubles.
3/4 hour, 3/4
Every 3/4 of an hour, it doubles. So like basically every 45 minutes, this thing would double. So 45 minutes, it's doubled. Oh, what's 45 minutes times 2? An hour and a half, it's doubled again. 2 1/4, it's doubled again. Okay. Let me just make sure everyone's got this before I move on, because this was really key. This 3,000 right here, you have to divide it away first before you do common bases. So divide the 3,000 away. I picked an example where the 16 right here actually can be a common base. So like 2 to the 4 is 16. Cancel the 2's. Gives you 4 equals 3 over x. Does everyone get how I turned that one into this one here? Okay. Take the x, times it up top here. So the x is up top now. And then divide by the 4. So really these guys are flipping places.
It says 15 instead of 60.
We have another method I'm going to show you later. But there is a way of doing it. Questions on that? Okay. Okay, another example here. Yeah, I mentioned before, there's a lot of like overlap with biology. I don't know if you guys ever do this in bio, but if you keep going, you may one day do this. So to figure out a thyroid deficiency, they put iodide in your body. And I don't know if you've ever heard of this before, but this radioactive iodide, it's not good to keep it in your body. Thank goodness, though, it has what's called a half-life. Have you guys ever heard this term before? Okay, what a half-life means...
Darian Atwood, can you please come to the office? Darian, please come to the office.
What a half-life means is that it keeps getting cut in half. So like if you start with 10, after a while it gets cut down to 5. And then it gets cut down to 2.5. And then 1 1/4. And it keeps getting cut down in half and half and half and half again until eventually your kidneys have filtered all of it out. Well, almost all of it out. If you keep cutting it in half, will it ever fully be gone? Not. I mean, eventually, yeah, it's basically gone. But does that make sense? Like, that's what your kidneys will do. It'll filter out this iodine, half, and then another half of it, and another half. Okay. So my question here is, how long should only 25% of the iodine be left? Like, how do we figure out when there's only 1/4 left? So let me try building an equation here. If something has a half-life, it keeps getting cut in half over and over and over again. What's the base going to be then? 0.5, yeah. So 0.5 is my base. What does that mean my graph looks like? Yeah, decay, which hopefully makes sense. This is going to be your iodide, and this is going to be time. And hopefully your kidneys will slowly but surely filter out the iodide, because otherwise that's not good for you, right? You don't want that iodide still in your body 10 years later. So, next question here. It gives us the half-life of 8.2 days. So basically, every 8.2 days, your body is able to get rid of half of the iodide in it. So here's my question. Is the 8.2 the top number or the bottom number? Because it was a half-life, so it keeps getting cut in half and in half and in half.
Should be bottom, because that's
So what's a full life?
full life it doesn't die.
Okay, can I come back to your question in a second here? Okay, you guys are right. The 8.2 would be on the bottom. Okay, so let me try to explain that one first, and I'll come back to Laramie's question.
Because if you have 8.2 days.
Okay, so probably the best way of putting it, if it's been 8.2 days, so if x is 8.2, 8.2 divided by 8.2 is 1, which means that you would now cut the iodide in your body in half once. So the 0.5 means you cut it in half, and then the 8.2 over 8.2 means it's cut in half once. What happens if x is 16.4? Then it's 2, which means you've cut it in half twice. So you've cut it in half once, cut it in half a second time. Okay, can I finish on that thought though? You're right, though that will be the answer. What should the y-intercept of such a graph be? Like the iodide at the top here, what amount of iodide would you start with? That's a good example. Why don't we start with 100%? Like, why don't we make this the percent of iodide? And you start at 100%. So the 100 should be a good number to go here. And what we're going to look to do is try to figure out when this now equals 25% left. Well, because isn't 100% like where, like, as you draw a graph here, when you start, you're going to have 100% of the iodide in your body. And slowly but surely that percentage of iodide will drop down until there's nothing left.
It'd be 0.25.
Well, okay, if this guy's going to be 100, this guy's going to be 25. The other option? Yeah, the other option, though, is you could write it like this. 0.25 equals 1, 0.5 x over 8.2. Both of those are valid.
So you can keep it as like a percent, or you can go to a decimal.
But you got to be consistent. This guy has got to be a percent, and this guy's got to be a percent. Or this guy is a decimal, and this guy's a decimal. But you can't do one of each.
Okay.
Laramie, in doing that, did I cover your question as to why this was a 0.5? Okay. So it's called a half-life, which means that like every 8.2 days, the amount of iodide in your blood is cut in half. So let's say you started with 100%. So like up here at 100%.
Yeah.
When will it be down to 50%? Well, it'll happen after 8.2 days. And then after another 8.2 days, it'll cut in half again. And another 8.2 days, it cuts in half again. Until like years later, it's finally dropped down. Is there still trace amounts of iodide left? Yeah, but like it's been, like your kidneys have filtered it out half at a time, half at a time, half at a time, until the point where there's basically nothing left. So this phrase right here was the key to know that this was a 0.5. Okay, next question for you. If you're using this guy right here, can you leave that 100 sitting there? The answer is no, you got to get rid of this 100. If you divide by 100 though, wouldn't that just make it this equation right here? Perfect. So if you did this equation here first, it doesn't matter because you got to divide this 100 out.
Why can't we use the 100?
Okay, because we want to give these guys common bases, and if there's a 100 sitting right here, we're not quite ready to give common bases yet. Now if there's the number 1 right here, do we need to write this number 1 anymore? Okay, so let's just skip that. Let me just write this further down here. 0.25 equals 0.5 to the x over 8.2. Now these numbers right here, I can make them into exponents with a couple of tricks here. 0.25 is actually 1 over 4. And 0.5 is 1 over 2. Okay, so this guy's 2 to the negative 1. And this guy is 2 to the negative 2. That's the trick to this one here. Okay. 0.25 is 1 over 4. 1 over 4 is like 2 to the negative 2, because it's like 2 squared.
How do you know, like, it'll be 2 to the power of negative 4, whatever?
How do you know these things?
You'll recognize them, hopefully. Like if I give you 1 over 10, you could call that 10 to the negative 1. But if I gave you 1 over 9, you could call it 9 to the negative 1. Or you could say, well, that's really 1 over 3 squared.
Well, why can't we call 2 to the power of negative 2, 4 to the power of
This one right here, you could have called this 4 to the negative 1, but then it wouldn't have the same base as this guy right here. Because this guy has to have a 2, and this guy also has to have a 2. So then our next step here, we can cancel these 2's. That's the key. Like we could call this another something there, but that doesn't help us if we can't cancel them.
So like if we were to be like integrating like 4 to the power of negative 1, how do we know how to change it to that?
Well, hopefully you recognize that 4 is the same thing as 2 squared.
Yeah.
Like hopefully that's something you recognize there. So then if you have 4 to the negative 1, it would be the same thing as 2 to the negative 2. They're both just negative then. Does that help?
Yeah.
Okay. Heather.
Can you kind of avoid dealing with all the like fractions and reciprocals and like negative exponents and stuff by just finding like the common base from 0.25 as 0.5 squared?
0. So what did you do?
I just put 0.5 squared is 0.25.
Oh, okay. Yeah, that would work too. That would work. If you see that, feel free to do that.
It's kind of the same thing as that minus.
Because, yeah, minus the negatives. Because here's what you'll get. I got negative 2 equals negative 1x over 8.2. And you probably had positive 2 equals positive 1x. Yeah. So just times your 8.2 up over here. And then it's negative 16.4 equals negative 1x. Divide by negative 1. X is 16.4.
Okay, so I have a question about that.
Okay.
Because I did mine except for I put like negative 1 and then bracket x over 8.2, so then like
You did
I
like this?
normally apply negative 1 to both.
You only apply to one or the other then.
Okay, because yeah, I got down and it was like
You get a negative number?
changed it into a positive, but then I was left with negative x, so I would have had to multiply by negative 1 anyway, and then that would not be right. So
Does that make sense? That negative 1 that applies to either the top or the bottom, but not to both, because 2 negatives would cancel and make it a positive.
Okay.
Does that make sense? Okay, one last example, and I'll stop talking for the day. There's one more thing you may need to be able to do. And some of you guys saw this last week. In your calculator has the ability to plot a table of values. Okay. Out of curiosity, how many of you were here Friday? Who's seen this already? Okay, so a few of you. Okay. We're doing that thing. Okay. If you know how to solve this question because you're here on Friday, feel free to get started. Because I think you might be able to solve it on your own.